3-2, polynomial functions of higher degree. We're going to do transformations. We're going to talk about the leading coefficient and what it does to a polynomial. Real zeros, finding zeros. How do we go about doing that? We're going to talk about something called the intermediate value theorem, which is actually, we talk about that again in pre-cal and calculus. So here we're looking at a polynomial function. So things you need to know about polynomial function. It's continuous. Continuous means if I was to draw a polynomial function, I can draw it with one smooth curve without ever picking up my pencil. There's no breaks in it. There's no holes. It's one smooth curve. Okay. This would not be a polynomial function. What would you call this? Piecewise function. It says what it is, right? So a piecewise function, though it is possible to have a piecewise function that is continuous, right? If these 2 points happen to meet, that piecewise function could still be, even though it's a piecewise function, it's still not a polynomial. So some other things we'll talk about the polynomials on the next screen. Only smooth turns. You will not see any sharp turns, no corners. Everything is very smooth. Even if it was x to the 22nd power, which would be a very, very steep growth. Actually, it's kind of flat at the bottom. 27x squared would be very steep, wouldn't it? Okay, that hurt. Right? So polynomial functions. So far, we've got continuous, we've got smooth, no sharp corners, right? Okay. So this is what a graph would look like that's sharp, the absolute value, right? It's sharp. Is it continuous? Yes, I can draw an absolute value function without picking up my pencil. So this would be a continuous function, but it is not a polynomial function because it has a sharp turn. So we're going to talk about sketching these graphs by hand. And in a sketch, we're not really paying a whole lot of attention to necessarily where the turns happen at this time. We'll talk about that later in higher levels of math. But we want to get an idea of what this graph looks like, and we can tell that by looking at the leading coefficient and the highest exponent. That's going to tell us a lot of information about the way this graph appears. So we talked about this graph on the left the other day. We talked about what x to the 4th looks like, and y'all told me that it was flatter at the bottom. And I said, yes, it's flatter, but it goes up faster at the same time. And as you can see in this graph here, we have in light font or whatever you want to call this in the background, we have x squared, and then this dark one is x to the 4th. So it does appear to be flatter. It is not flat though, okay? This graph from negative infinity to 0 is always decreasing. And as soon as it hits 0, it starts to increase again. Understand that. It might appear to be flat, but that would involve some kind of a sharp turn. Okay. X to the 4th is a smooth curve nonstop. X to the 20th would look like this. Right? So it's even flatter at the bottom, but it goes up faster. Over to the right here, you see x to the 5th. Underneath x to the 5th, you see x cubed. The shape is the same, right? The shape is the same. Okay. So what do you notice the difference between the two? One's even and one's odd. What do you notice? Let's teach ourselves this lesson. Not necessarily the parabolas, because only if it's a monomial, okay? If it's an even powered monomial, it's going to take the shape of a parabola. Yes, yes. If it's a odd degreed monomial, it's going to take the shape of x cubed. That's a true statement. But I don't want you to think that if you see x to the fourth, it's going to be a parabola, because if I throw an x to the fourth plus x cubed in there, it's not a parabola anymore. Okay. Any other observations on these two graphs? Okay, it's not as easy to see here, but the x to the fifth is inside the x cubed. X to the fifth is over here, x cubed is on the outside. So even x to the fifth is going to be steeper. It's harder to tell here. Okay. Any other observations? Okay, so if we're dealing with a monomial, in this case, yeah, if we're dealing with a monomial, and even when only touches the x-axis, where an odd crosses the x-axis, what'd you say? The right one being, what do you mean a constant? It only touches the x-axis once. It's a straight pass through. Okay. Yes, this is not a horizontal line in the middle of this. Just the an odd degree polynomial is always increasing. Yes, yes. Okay, let's move on and see if y'all tackled anything we're going to talk about. The bigger the value of n, the flatter the graph near the origin, but still it's a smooth curve. We've already talked about that. So let's look at the graph of negative x to the fifth. In what you know so far, my camera's not tracking. How? That was probably not politically correct to say that. Is it tracking now? Thank you. Okay. So what do you think negative x to the fifth is going to look like? Why is it decreasing? Okay. So if we think about, I'm going to call it g of x. If we think about g of x being the parent function of x cubed, we know that that graph looks something like that, right? That's what it looks like. So negative x to the fifth, what's the negative sign going to do? Flip it across the x. And what's the exponent of 5 going to do? Make it will be steeper. What else? In the center of it, it's going to be flatter, right? So more spread out. Okay, I'll uncover it in just a second. I'm not going to draw it. I'm going to let you see the actual drawing. Let's talk about part B. What's it going to look like? Flatter at the bottom, left one. Okay, you said, yeah, similar shape as x squared, kind of this parabolic feel, right? Yeah, great job. Wrong one. It's that one, right? Okay. So because the degree of f of x equals negative x to the fifth, it's odd. It's going to be similar to x cubed. But like you said, it's going to be a little flatter because the 5 is higher than 3. And also, like I said, it's going to be flipped across the x-axis. Not a big deal. Okay. Moving on to the part B. Exactly like you said. It's got that parabolic fill. It's flat at the bottom. It's been shifted left 1. Any insights or thoughts so far? Pretty simple. Just like everything else with you in this class. Okay, leading coefficient test. We'll talk a little bit about what is the leading coefficient? The A. Tell me more about it. It's the A. What else? What makes the leading coefficient the leading coefficient? How do you know which coefficient is the leading coefficient? Okay, it's the term with the highest power. It's the term with the highest power. Okay, now we call it leading coefficient because when we write a polynomial in general form, we write with descending powers. If I put a polynomial in general form with descending powers, that would mean the first term would have the leading coefficient, right? So if I had, nice. If I had f of x equals 3x squared minus 5x to the 5th plus 4. What's the leading coefficient? The leading coefficient is -5. But that's not written how it should be, is it? I would want to rewrite this in general form as okay. Now my exponents are in descending order. Now it's obvious that leading is this guy right here. So the leading coefficient for this one is -5. Okay. Okay, so in the graphs that we looked at, both graphs would rise or fall, wouldn't they? Forever. Correct? Look at the -x to the 5th. Then we go back two slides here. Okay. Nope, it's not slides. It's down here. Yeah, let's look at this one. Okay. What's that one doing on the left side? Okay. When I'm talking about whether a function is increasing or decreasing, we only read left to right. When I'm talking about what is the function doing on the left side or the right side, I'm talking about, let's go away from the middle. Okay. So what is this graph doing as we go to the left? It's increasing for how long? Forever. As we go to the right, what is this function doing? Decreasing forever. Okay. Going to the left, what is this function doing? Increasing forever. Going to the right, increasing forever. That's what this is talking about. Both graphs eventually rise or fall without bound as x moves to the left or the right. Whether the graph of a polynomial function eventually rises or falls can be determined by the function's degree, even or odd. So when it was even, what were the ends doing? Let's go back to the even one. What are the ends doing? They're both increasing. What if I put a negative sign in front of x to the 4th? So when it's even, what can you tell me about the ends? Okay. When you're think about even, think about going in pairs. Okay. As a couple, they're going to go together. Okay. As a couple, they're going to go together. But when you're odd, when you're single, you can go your own way. Okay. Does that make sense? So when a function is odd, what do the ends do? Opposite directions. Okay. That's important to know. Some of you are better at odd, some of you understand even. Okay. Okay, moving on. Leading coefficient test. As x moves without bound to the left or to the right, the graph of the polynomial function eventually rises or falls in the following manner. So we're going to move on and see what it looks like. We've already talked about it. If a function is odd, if the highest degree term is odd, think about that's the term that has the power. Okay, and that one that I wrote down right here, the highest degree, even though there's an odd here and an even one here, the highest degree is where the power is. The highest degree is going to take care of what's happening to this function. So when n is odd, the graph will look like this. I don't know what's going to go on in the middle, but because it's odd, we're going in different directions. We could go down on the left and up on the right, or we could go up on the left and down on the right. What's going to change that? The sign of the leading coefficient, right? If it's even, oh, these are both odd. So this one's an odd one. This is probably a third degree, could be more, but I know it's at least a third degree, and I'll talk about how I know that later. So this is at least x to the third, but I know it's odd. And this one here is at least x to the fifth. I can tell just by looking at it. It could be more than 5, but it can't be less, but it's at least x to the fifth right there. Leading coefficient on this one is positive or negative? Positive. Leading coefficient on this one is negative. All right. This one only crosses once. Y'all trying to figure it out? When it's even. Yes. Exponent. Yes. Yeah. N is the exponent. When n is even, when the exponent is even, we're either both going up or both going down. That first function is at least a fourth degree. Could be 6, could be 12, can't be 2. It's got to be even. It's at least 4. And this one is at least 2. Okay. Questions so far? That'd be a line. No, it'd be a line. L-I-N-E, not lying. I be lying. Okay. We're talking about in behavior only. In behavior only. Letter A. What is the leading term? The leading term, negative x cubed. What is the leading coefficient? -1. What is the degree of the polynomial? The degree is 3. How do we know the degree is 3? That's the highest powered term. Okay, I'm just throwing vocabulary, guys. Okay. So, because this function is odd, without paying attention to really what the function is, we know it's odd. Tell me what the ends are doing in general. Opposite directions. Perfect. Now, what's it look like? Left side, what's going on? Okay, so it's increasing to the left. What's it doing to the right? Decreasing on the right. There you go. That's what function A is doing. I don't care about what's going on inside. All we're talking about right now is what is the end behavior doing? Okay. I might sometimes call this an up down. Reading from left to right, it's up on the left, down on the right. So if you hear me say up down, that's what I'm saying. I'm saying it's up on the left, down on the right. That makes sense? Okay. Reminds you of athletics, right? Time for some up downs. Why don't they call them down ups? Because when you do up downs, you actually start in the up position. I'm just throwing that out there. I've never seen a person start. Okay, part B. What is the leading term? X to the fourth. What is the degree? 4. Leading coefficient? 1. Even or odd? Even, which means the ends go together. In this case, it's an up. Is it an up? Okay. That's an up, and that's another up. That's an up. Now I'll do a down. Okay. And that was freaking recorded. Okay. And me saying that was recorded. Okay, anyway. Part C, degree. Degree? 5. Leading coefficient? Leading term? X to the 5th. It'll be uploaded.
Let's go.
Okay, it'll be on YouTube. Okay, even or odd? Odd, which means the ends go their own way. Okay. In this case, down up. Okay. Okay. I'm going to go on to the next slide and go fast. If y'all want to take snapshots, it's going to be part A, part B, and part C on 3 different pieces. Okay. Here's part A. They actually graphed it, but all we were doing was talking about what the ends are doing. Okay. And that's what we said. Part B. There it is. Up. And part C. Down, up. Questions on those? Okay. In example 2, the leading coefficient tells you only whether the graph goes up or down on the left or the right. That's all it tells you. Other characteristics such as intercepts, minimums, and maximums must be determined by other tests. So all we know right now is what's happening on the ends. That's all we know. Zeros. It can be shown that for all polynomials, function f of degree n, the following statements are true. If the degree is n, it will have at most n real zeros. Number 2, y'all kind of got onto this a little bit. The graph will have at most n minus 1 turning points. Who said something about turning points? Several of you. Okay. So think about it. A parabola, x squared. How many times does it turn? Once. It's just x, the parent, right? It's decreasing. It's now increasing. 1 turn. Okay. X cubed. How many times does it turn? The parent function x cubed. How many times does it turn? 0. It's always increasing. What does it say here? The graph has at most, right? If I was going to graph the graph of f of x equals x to the 22nd power, how many times does it turn? Once, right? It only turns once. Okay. Do what? It says at most. Y equals x squared looks like that. Y equals, that's not a Y. Y equals x to the 22nd looks like that. It's still only turned once. Okay. I guarantee, and think about this, I guarantee an even function turns at least once, always. Why? If it's up, up, it's got to turn. If it's down, down, it's got to turn. How about an odd function? Doesn't have to. How about this? I guarantee all odd functions will cross the x-axis. Guaranteed. If it's an odd function, it crosses the x-axis. Agree or disagree? It has to. Right? Can I guarantee that all even functions cross the x-axis? No. Okay. A U at the bottom or U at the top? Okay. Turning points are called relative minima or relative maxima. Turning point is where a graph changes from increasing to decreasing or vice versa. Here's something we've talked about in the past. We're going to talk about it again. There's a strong connection between graphical and algebraic approaches to problems here. You've heard the term zeros, solutions, factors, and x-intercepts, right? And in the past, we basically said, yeah, they're all the same. Yeah, they are. Kind of. Okay. They do have a slightly different meaning. X equals A. That A is the zero of the function f, meaning if I take A and plug it into the function, the output will be 0. Okay. X equals A is a solution of the polynomial equation f of x equals 0. That's what I just said. So 1 and 2 are very closely related. Look at number 3. A is not a factor of a polynomial. A comes from x minus A, because if you set x minus A equal to 0 and solve for x, you would get x equals A. Okay, so x minus A is a factor. The x-intercept is the point. A point is a coordinate of exactly where the graph crosses or touches the x-axis. So an x-intercept is a point. But notice it has an A in it, right? That is the x value of the x-intercept. Okay. I know some of you are writing, but I'm going to move on anyway. You can come back and look at the video to write the rest of those down. Find all the real zeros of negative 2x to the fourth plus 2x squared. Then determine the maximum possible number of turning points. Okay. What's the degree? Huh? 4, which is even. So what are the ends going to do in general? Go together. In this case, they're going to go down. Okay. How many turning points at most does this guy have? At most, how many does it have? 3. At most, it has 3 because that's n minus 1, right? Okay. To find the zeros, we set it equal to 0 and solve, right? Okay. So how would you go about solving negative 2x to the fourth plus 2x squared equals 0? What would you do? Can't do a vertex form. That's for quadratics. This is not a quadratic. This is a 4th degree polynomial. But thanks for trying. Yes, I could factor out a 2x squared, but I would actually want to factor out a negative 2x squared because the leading coefficient is negative, right? So if I was to factor out a negative 2x squared, what's left? Okay. Does x squared minus 1 factor? I'm hearing yes and no. One of you are right. It's a difference of 2 squares. It factors into x plus 1 times x minus 1. Okay. So based on this, what do you see for the zeros? What are the real zeros? Okay, remember, you set all factors to 0. Negative 2x squared equals 0, or x plus 1 equals 0, or x minus 1 equals 0. 2x squared equals 0. That's true if x is equal to 0. X plus 1 equals 0. That's true when x equals negative 1. X minus 1 equals 0. That is true when x is 1. Okay. How many zeros are there? 3. 1, 2, 3. I'm going to throw this out there. This is a 4th degree polynomial. A 4th degree polynomial must have 4 solutions. And this one does have 4 solutions. The solutions are 0 and 0 and negative 1 and 1. But we don't say the 0 twice. Okay, it's not a plus or minus. This is called a double 0. Okay, or it's a 0 with a multiplicity of 2. Okay, because really, doesn't x squared factor? X squared can be factored into x times x. So I really could say x equals 0, or x equals 0, or x plus 1 equals 0, or x minus 1 equals 0. The degree of the polynomial will tell you how many solutions it has, but they're not necessarily all real though. Okay, this one actually does have 4 real solutions. It just happens to be that one of them has a multiplicity of 2. Okay, what were you gonna say? No, there'd be 3 zeros. Yeah, and we'll talk about multiplicity later on. I'm just kind of throwing that out there as it surfaces. Okay, moving on to see how they finished solving this problem. They did exactly what we did. They factored out the negative 2x squared. They factored and they got the real zeros of being 0, 1, and negative 1. Because the function is a 4th degree polynomial, the graph can have at most 3 turning points. And this graph actually does have 3 turning points. Okay. A polynomial function is in standard form when its terms are descending order of exponents from left to right. I get confused with their use of the term general form and standard form. Because didn't they just say standard form for a quadratic was vertex form, which is not descending power, right? They called that general form. But now we're saying standard form for a polynomial function. So whatever. Before applying the leading coefficient test to a polynomial function, we have to make sure the function is in standard or general form. And I talked about that earlier today anyway. Intermediate value theorem. The intermediate value theorem is used for finding zeros. In this case, they're showing a picture that does not show 0. But here's what they're saying. They're saying if I have some point at A that's f of A, if I have another value B to get at f of B, if it's continuous, there must be another point in between there, is what it's saying. Okay, so here's what's going to happen. If I have a function, if I said that f of 1 was 4 and f of 3 was negative 6, and it's continuous, does that graph cross the x-axis? if f of 1 is 4, f of 1 is 4, f of 3 is -6, does it cross the x-axis? How many times? At least once. At least once. Okay. It could do that. Pretend that's a function. Pretend that passes the vertical line test. Does that make sense? But I guarantee in order to get from 4 to -6, I'm going to hit 0. That's the intermediate value test right there. Okay. I'm going to move on to the next slide. Yeah, y'all can read that if you want to. when they start putting theorems in words, it's basically what I just told you. Okay. Another thing, if I said that if f of 6 equals 12 and f of 8 equals 15, is there a number between 6 and 8 that will get me a value of 14? Is there some number? Can I plug some number in here and get 14? Right. It could have a decimal. It could be a nice number. But does this happen? Well, yes, because 14 is between 12 and 15. That's intermediate, right? Intermediate means between. That's what's going on with the intermediate value theorem, okay? Lots of wordy words there. Here's an example. Here's a function. F of -2 is -3. F of -1 is 1. Does it cross the x-axis? It has to. It has to. Okay. And by using this, we can actually approximate zeros. Okay, without using a calculator, I can get closer and closer and closer and closer and closer to a 0. No, because it's got to cross 0, so it's got to touch. Yeah. So how would you go about approximating a 0 on this guy? You would take f of some number and plug it in and see what you get. If we don't have the ability to graph, right? I'm going to wrap this one up tomorrow. I will not have time to do the practice problems like I have in the past. I'll wrap this up tomorrow and we'll jump into 3-3. Okay.
Sounds like you're taking